Hey, it's working. Right, hello, good morning. Oh, it's actually afternoon now. Good afternoon, year 10. I always get that wrong, don't I, even in lessons. So this is a video to help you with the work that I've been setting you on energy changes. Okay, so there's a few different lessons there. I'll just review what I've sent you anyway. You can see, by the way, the textbook cutouts haven't come out that well. By the way, I'm on my laptop here, that's why you can't see it, but whatever. And the laptop has frozen, so... Oh, that's my wife playing with my son, by the way, in the background. So you can see the first couple of lessons are on exothermic and endothermic reactions. There is a required practical that goes with that, but okay, we can't do it, so sorry. But I reckon exothermic and endothermic reactions are fairly straightforward. Exo gives out heat, endo takes in heat, that's pretty much it, okay? The second lesson is on using energy transfers from reactions, basically I don't know, hand warmers will warm your hands up. I mean, again, that's fairly straightforward. I don't think we need a video on it, to be honest with you. Then lesson 3 is reaction profiles and bond energy calculations. Is lesson 4. Lesson 5 is on chemical cells and batteries, which again, do we need a video on it? I don't know. So I reckon those two we need a video on. So I thought I'd do a video for you to help you with just those two bits. Right, so let's do it. Let's make a video. Okay. Now, as part of this, I'm going to do a little example. You can do that at home if you want to as well. That'll be fun. It's one I don't think you've seen before, so we'll see if that works. So, first things first is bond enthalpy or bond energy calculations, right? Which is lesson 3 on the plan I've set you, reaction profiles. That's called. So, what you're actually doing here is you are producing a graph, which I may or may not have mentioned in lessons, I don't know. This I have a little whiteboard, but it's my son's whiteboard. You can see there's little squiggles on there. He's 2, we have it as a little toy for him. So, what you're going to do is produce a graph, and it's just a sketch graph, and it just shows progress against energy. I'll draw it that way so I can actually fit it on the screen. Progress against energy, okay? Progress of what, I hear you ask? If I hear you say anything at all. Somebody probably already staring in space. But that's just typical lesson, eh? Yeah, there we go. Right, anyway, so what you're actually looking at is the progress of the reaction. Basically, you think of it as time. How far along in the reaction are we? So, we start off in any reaction with something called reactants, starting materials, okay? So if we had a reaction that's, I don't know, let's say that we're doing the reaction of methane plus oxygen forms carbon dioxide plus water, okay? The reactants are these two things. So what we're saying is the energy of those two things is there. Let's pretend they've got that energy, right? Now, to start off a reaction, what do you need? What do you need to do? Well, if you think about it, methane is the stuff that CH4 there, is the stuff that comes out of the gas taps. Does the methane just react with the oxygen in the atmosphere? Does it just happen automatically? You turn the gas tap on, it just starts reacting nicely? Well, if you said yes, you were wrong. No, they don't just start reacting. They need something to get them to start. What do they need? Well, we need to light a match, don't we? You know, we need to set it on fire. So a match has got a little bit of fire in it, and that fire is a form of energy. Very good. Well done. I knew you knew it. You're a very clever bunch, yeah. So what we're actually going to say is that before the reaction gets started, we have to increase the energy of our chemicals. Okay, we are giving the chemicals some energy. I rubbed out the word progress there. Whoops. Okay, they've got a little bit more energy than they had at the start. We call that the activation energy. Okay, I may have mentioned that in lessons before. So saying it goes up, there, activation energy. Right? And this arrow going upwards is the activation energy. Notice it's an arrow going upwards, so make sure you understood that, right? Then what happens is, eventually, that's the energy required to break those chemical bonds. So then what happens is the chemicals will come back together, form some new chemical bonds, and that will release some energy. Okay? So I'll draw that going downwards. So that means the chemicals have actually released some energy when they form this. So start out here, they've got that energy. You give them some energy, and that breaks all the chemical bonds. You end up with like carbon, hydrogen, oxygen, atoms on their own, then those atoms rearrange, come together again, and that releases some energy. So the chemicals have less energy. They have given it out to the surroundings. They have transferred energy from the chemicals to the surroundings. And that comes here, and that is the energy of the products. So they are there. Products, reactants, activation energy, products. Okay? Now hopefully you can see that the lines are not equal in size. That's not just because I'm bad at drawing, that's actually on purpose. And that is because there is a difference here. It shows that overall, the reaction releases more energy than it takes in. It's exothermic. Okay, there's a little arrow going down there, it's exothermic. The overall energy change is exothermic. Okay? So what you can say is more energy is released when the products form than is required to break the reactants apart. Or another way of saying it, energy in bonds broken. Okay, so think about it as, I don't know, it's not very neat, but energy in, bonds broken. Energy out, bonds formed. Okay. Okay, so that one, energy is out, bonds form. So if less energy is required to break the bonds than is released from forming the bonds, overall, the overall energy change will be negative, i.e. overall the chemicals have lost energy to the surroundings, so they have a negative energy change. And therefore, it's exothermic. That is on lesson 3. Now, just continuing with that, if on the other hand, we start off with our reactants, just there, I've cleared everything off, and it still has an activation energy. These reactions will always have an activation energy, and then it goes down, but it only goes as far as here. Okay, you can see that actually the energy in the chemicals has gone up overall. Okay, that's called the overall energy change, and that has gone up. If the chemicals have taken in energy from the surroundings, then that must be an endothermic reaction. Okay, so think about it. If you have an endothermic reaction, it's going to feel cold because the chemicals are taking in energy from the surroundings. Okay, taking in heat energy. Right, so that is basically lesson 3. You'll see at the end of that textbook page there are some examples to try. I would strongly recommend trying those examples before moving on. It's something that people often struggle to kind of get their heads around, so I would strongly recommend that. The thing to make really, really clear, a common misconception is, so the exothermic reactions, the energy ends up going down, the energy of the products is lower than that of the reactants. Endothermic, the energy of the products is higher than that of the reactants. If, however, people are doing, I've seen all sorts of things. Well, I've seen people have negative activation energy, so it looks something like that. It goes up like that. That's just ridiculous. There's no way. If it's a negative activation energy, it's just going to happen anyway. You don't have to give it any energy. It's just going to happen spontaneously. That's called spontaneous combustion. It's not going to happen. It's got to go up. Otherwise, what's stopping it from happening? So yeah, I've seen that before. I've seen all sorts of crazy things. Just draw it the way I've shown you to draw it. A bit of practice, it'll be easier. Now I'm looking at the time of this video. It's already like nearly 10 minutes long. So what I'm going to do is do a separate lesson, do a separate video for lesson 4. I would suggest you watch this video. Make sure you've done all the stuff from lesson 3, which is on reaction profiles. Do the questions, do everything I've set you. Then go to lesson 4, and I'll go through an example from that. I'd recommend reading through it first, just to be on the safe side. Right, so I'll do you another video then. Peace out.